Okay, so I wanted to take a little bit of time to work through a couple of problems just to, maybe give you guys a little bit more of a chance to kind of work through some practice or maybe hear my thoughts on something or how I work through a problem or what I do when I approach some of these synthesis problems. And so, we'll I don't know how many of these we can do or ought to do or should do, but we'll as always we'll just keep going as we can through this semester, right? So anyway, here's the first problem. At this point, you guys should copy that down and then answer this on your own, right? You guys should be able to work through this on your own, and then come back and maybe listen to me, give my thoughts about it, and check your answer, that kind of thing here, okay? So pause here, and then we'll be, then come back, and we can finish this up. But all right, so first thing is, when I see an epoxide there, right, I've already labeled it in the red and green. Truth be told, I had to start this video over a couple of times, and I forgot to erase it. So I kind of gave you guys a hint there, but that's fine too. And so what I was just going to say there, when we're dealing with an epoxide, we're going to be involving those two carbons there, either the red or the green carbon. We talked about the mechanism that's involved, whether it's attacking the more or the less substituted side, whether we're under acidic or basic conditions, and that's going to impact which of those two carbons we're going to attack, right? And so what's useful is if we take a look at those two carbons, right, we see that the green is the more substituted side. That means whatever was added came in at the red carbon, which is the less substituted. If we add something to the less substituted side of an epoxide, that means it's under basic conditions. Do you guys catch all that? So what I mean is this, right? If we go back through had the wrong tool selected there, right? If we go back through and think about this, right? We have those two red hydrogens there to begin with. And then we know that we had to bring in another hydrogen, and we brought that into the less substituted side of the epoxide, so we know this has to be under basic conditions because that's what happens under a basic ring opening, right? So we have to bring in a basic hydrogen, right? And so that's the question. How do we have a basic hydrogen? Really the question comes down to, what makes a good base, right? And that's one of these fundamental questions in chemistry, especially organic chemistry. That's why you guys spent a whole chapter on it in the first semester there, right? It's, figuring out what an acid is, what a base is, how to make something a better acid, how to make something a better base, right? So really a base, right, is just a localized negative charge, right? That's probably one of the, I always hate to say simplest definitions, but maybe one of the simplest definitions, right? So we're looking for something with a localized negative charge. We know we have to bring in a hydrogen. How do we make a localized negative charge on a hydrogen? Well, we're just bringing in an H minus. Okay, now we're getting somewhere. All right, so remember when we're talking about H minus, right, this is a hydride. Oh my goodness, I can't spell this morning. Let's try this one more time and see if we can get something effective written down. Okay, so that's a hydride, right? Now we've dealt with hydrides quite a bit. We know a couple different sources of hydrides that have different applications depending on the reaction that we want to affect, right? The transformation that we want to affect. And perhaps the simplest one or the best one in this case is going to be our buddy LAH, right? That's lithium aluminum hydride. Okay, and if we know that if we put lithium aluminum hydride together with an epoxide, right, it's going to ring open that epoxide and attack, right, the hydride's going to come in and attack at a less substituted side. Okay, now when we use LAH, it's always going to be in conjunction with some kind of acidic or some kind of workup, right? So whenever we see LAH, we know we're always going to follow that up with some kind of workup there. Sometimes it's acidic, sometimes it's just water. What's the difference? On paper, the difference isn't too much, but we got to be careful, right? If we come back and do an acidic workup, if we have other groups that are susceptible to maybe acidic hydrolysis or something like that. If we've got amines around, we don't want to throw acids in there because you're going to end up protonating those and things like that. So does it matter in this case? No, right? You could use water. You could use, some acidic, generic H3O plus, something like that. It's not really going to matter in this case. But when you use LAH or when you use most hydrides, to be honest, you're going to have to follow that up with some kind of acidic workup just to make sure that we end up protonating what we need to protonate, right? Okay, so that's enough yammering for that. Let's do the first part here. So I'll just kind of move that note up here. So we will take this, right? Step 1, LAH, right? And step 2, workup. So then, all right. So we know that we're going to have that. We're going to add that red hydrogen there. Right? Let me write this a little bit bigger. Apparently I'm having trouble writing cleanly this morning. What's the mechanism? How does this look? You guys should be able to do that, right? A hydride comes in, attacks the less substituted side, and pops open, right? That's ring opening under basic conditions, okay? So after the LAH is added, right, we just have the alkoxide there, right, the O with a negative charge. And this is where bringing in the water, right, the H2O is going to be useful for us because now we're left with the alcohol, okay? So if you just have LAH around, you end up with O minus, right? Because it's such a powerful base, it's going to just deprotonate everything. You're not going to generate an alcohol when you have LAH around, right? Okay, so now we have an alcohol, and we need to get an alcohol transformed into a ketone, right? So this is an oxidation reaction, right? In green we have an oxidation, right? Now when you're dealing with oxidations, we always have to pay attention to what, if you guys have listened to some of my lectures for the first semester of OChem, or if you guys have taken OChem before with me for, I don't know, it could be, I don't know, right? What I tend to call these are flavors, right? And so what I mean is, what flavor of functional group do we have? Is it a primary, secondary, or tertiary alcohol that's there, right? Because that's going to be really important when we're dealing with organic oxidations. A primary alcohol we have to pay more attention to than a secondary or tertiary, okay? So with primary alcohols, we have to pay attention to, I guess, what we would call over-oxidation, taking it all the way into the carboxylic acid. Secondary alcohol, we don't really care. They're not that, how do we want to say this, susceptible to over-oxidation, right? We can't turn a secondary alcohol into a carboxylic acid under standard conditions, right? In fact, off the top of my head, I don't think we learned anything in this semester where we can affect that transformation, right? So when I am looking at taking an alcohol into a carbonyl, the first thing I look for is what is that alcohol, right? Is it primary, secondary, or tertiary, okay? If it's tertiary, then, forget it, we can't do it, right? But primary versus secondary, then, we have to sit there and pay attention to that, right? So secondary alcohol into a carbonyl, that's not that selective. We can't over-oxidize that, so we can pick our favorite, right? So secondary into ketone. Okay, that's what we have to do. There's a million ways of doing this. Okay, so we just have to pick one. If we were in the lab, right, we'd probably do a Swern oxidation with this, right? That's kind of our go-to standard, just because it's cheap, it's easy to do. We usually have all the stuff around. Right, there's Swern oxidation. We could use PCC, we could use PDC, that's pyridinium chlorochromate and pyridinium dichromate, right? Those are our two organic soluble chromate salts. That's kind of why they're used, right? And we run those in a solvent that water isn't around, right? And that's the key for this, right? Excluding water is the way that we get to selectivity, although, like I mentioned, for secondary, it's not really going to be a big deal. We could use the Desmartin periodane there, right? DMP, right? That's going to help. That could do something for us. You could use chromic acid. You could use, there's a million different ways of doing this. So honestly, in this case, you could pick any of these here, right? So I'm going to write, PCC because that's the least calories, right? That takes the less amount of the one of the least amount of effort for me to write that down on the screen. Okay. And so I had a couple email questions about, what are you going to ask on the exam and how are you going to ask stuff, and this is going to be, I wouldn't say a typical question, but this would be wouldn't be a bad question for an exam. But I'm not just going to ask you guys to give me this synthesis to get there. I'm also going to ask you guys to explain, right? Explain why you guys picked, your conditions, right? Why did you guys pick LAH? Well, we picked LAH because we noticed that the ring opening was under basic conditions because the alcohol got left on the more substituted side. That means the incoming base had to come in at the less substituted side. Why did I pick those oxidation conditions? It's not selective because it's at a secondary alcohol, so we can pick whatever we want to, right? Those are the kind of things that really give you an understanding of, do you know what you're doing with this, right? So that's going to be kind of the difference, right? When we're doing a take-home exam for organic chemistry, it's not just, not just fill in the blank, so to speak. It's also going to be explaining why it is, right? So that might be a good example here for that. Okay, do you guys catch all that? If not, the benefit of me recording these videos, you guys can always rewind and go back through it and listen to me at double the speed, right? Okay, so here's the next problem. So again, if you guys want to pause, copy this down, and then see if you guys can work this through on your own before you listen to me do it. That'd be fantastic. Oh, let me back up here for just a second. Well, actually, no, that's okay. Never mind. So if you guys are paused and you guys are back, pause again. Did you guys work through the mechanism for everything that you guys have in there, right? Now, we don't know the mechanism for every single transformation, but did you guys work the mechanism for all the ones that you do know? Well, gee, Dr. H, that's a lot of work. Yeah, I know, right? It is a lot of work. I get it, right? But there's no secret sauce to organic chemistry, right? It's practice, right? It's practice, and then as you're doing it, you stop and you ask why. Okay? Why does this happen? And if you do that, right, then you guys are going to be okie dokie at the end of the semester here, right? As you guys go through this. All right, so again, pause, stop, analyze, look, think, right? Put some notes down the first time you see something, right? So what we do notice is, right, here we've got, there's our tertiary alcohol, our tertiary carbon. We have an SH group bound to it. Ooh, okay, interesting. Next door to that, we'll mark it in purple just to really liven things up. Right, so in purple there, now we notice we have an alcohol. Okay, so adding an alcohol, that's not too bad. We can do that in multiple different ways. Adding a thiol group, we might not have talked about that too much explicitly, but one of these things to kind of always think about is that, sulfur on the periodic table is right below oxygen. And so what that means for us is that, they share a lot of properties. They're not identical, right? Of course, I didn't have to tell you guys that, that, right? They share a lot of properties, and so a lot of the reactions that work with alcohols work with sulfur, right? And so if we can add an alcohol, then, usually we can just swap things out for a sulfur, and for the most part, it's going to work the same. Of course, I'm generalizing things, right? There's certainly exceptions to that. One other thing to pay attention to is that the thiol and the alcohol are next door to each other, right? So we have a vicinal set of functional groups that we added to this. And that's a big clue, right? It's a big clue that these are vicinal to each other. They're next door, right? That means that this is, usually we had an epoxide happen somewhere in between there, okay? I'm not saying that's 100%, of course not, right? But if we have two functional groups that are next door, especially if one of them is an alcohol, that usually means we had an epoxide somewhere in there, right? And so my thought here is, we had something, right? We don't know what, but somewhere along the way, right, we had to have this, okay? I don't know how many steps it takes, right? But somewhere along the way, we had to have that. Because if we take a ring opening of this epoxide, we know we will generate an alcohol, And if we go back to the idea that we were just thinking about, right? If we have an epoxide and we do a ring opening, we will end up with vicinal functional groups, and we'll end up with one of those functional groups being an alcohol. You guys catch me on that one, right? When we ring open an epoxide, we end up with an alcohol, right? So if we work under that assumption, right, then we look at that green carbon and we know we have that thiol that is added at the more substituted side of this epoxide, right? We have the thiol that's added at the more substituted side of this epoxide. So what does that tell you? That means that this had to have been under acidic conditions, right? Acidic conditions. All right, so let's think here for just a second. Let's see if we can just fill in this last step here, right? So this last step, we know we have to add sulfur under acidic conditions, right, to ring open that. And so let's pretend we're in an alternate world for just a second, just for argument's sake. I genuinely don't know why I'm having trouble writing this morning. I'm going to blame my computer. My pen or my stylus here has been messing up. But anyway, so here we are in an alternate world. In the alternate world, I'd asked you to, make that compound there that I'm pointing to in red. Okay, so how would you do that? Well, that one's pretty easy. I would just take some H2O and I would add some kind of acid to it. And that would be acidic conditions, right? We worked through that mechanism in class, well, in lecture. It's in your book. It follows through with that, right? And we would end up with that. Now, if you guys rewind, I would say, well, okay, if we're trying to add a sulfur, usually it works the same way as with oxygen. Then instead of H2O, right, we could just add H2S and some kind of acid. Okay? You guys catch that? What's the difference? How's the mechanism going to change? There is no difference, right? So if you guys can draw the mechanism for the pathway in red, then you can draw the mechanism for the pathway in green there. Okay? H2S, right, versus H2O, not going to be a difference for those, okay? I'm highly recommending that you guys go through and draw the mechanism for this. All right. So good, we got that. Now we've got to generate an epoxide. So question, can we directly generate an epoxide from that alkane? And the answer is no, right? An alkane doesn't have any functional groups on it. Okay? So if we don't have any functional groups, then, well, we got to add a functional group to it. And there's really only one reaction that we know that we can add a functional group to something. And that is our good old buddy halogenation, Br2 and HV, right? And if we do that, wow. And if we do that, then we know we are doing radical halogenation. We're going to add a bromine to the most stable position for a radical to form, right? Tertiary position in this case. You guys should know that mechanism, and we should remember, stability of radicals trends the same with stability of carbocations, right? In general, again. Okay. So now that we've taken care of the problem where we didn't have a functional group to begin with, now we do have a functional group, we can ask ourselves a question again. Can we go directly from a halide into an epoxide? Well, the answer is no, right? Well, because here's what I'm really trying to do, right? The question is, how do we make an epoxide? Well, there's really only one way, right? There's really only one way that we learned how to do it. We have to start with an alkene, right? We have to start with an alkene. Ooh, okay. So if we have an alkene, right? If we have an alkene, we can make an epoxide from that. How can we do that? Well, that's our good old buddy, MCPBA, right? Metachloroperoxybenzoic acid. Is that the only way? Not really, right? There's another way, right, that we can, I'll mention it at the end here, but MCPBA certainly is, let's say, the most elegant way of doing it, right? So we have to generate an alkene before we can make an epoxide. All right, now back to the question. How can we turn a halogen, right, an alkyl halide into an alkene? Well, we sure can, right? But we got to be careful, right? We know we have to do an elimination, but if you notice, right, this alkene here is a terminal alkene. So we have to put in a strong base, right, a strong bulky base that will eliminate and form the less substituted alkene. Our T-butoxide will be probably our go-to choice. LDA, right, could be a choice here also. Either one of those, but T-butoxide will be just fine for what we're doing, right? Remember, we have the Hoffman versus the Zaitsev products for elimination, okay? So go back and take a look at your elimination mechanisms, or your E2 mechanisms there, and when we talked about, using a bulky base to favor the less substituted alkene, okay? So that's what we're doing. Got it? So step one, let me do this in black here, right? Step one, we have to do our halogenation. Step two, we have to eliminate to form the less substituted. Step three, we do an oxidation to form the epoxide. And then step four here, we do a ring opening of the epoxide, and that will add our two functional groups next door to each other. Okay? Fantastic. All right, we're going to take a quick break here while I load up the next question. So on your end, it'll take all of 3 seconds. On my end, it'll be a little bit longer, but I'll see you guys in just a second.